All right, next up we have Rampalli from Dartmouth.
Can everyone hear me okay? Cool. Hi everyone, I'm Rampalli. I'm a fifth-year PhD student at Dartmouth College. Today I'll be telling you a little bit about our sun and its chemistry and how that could be a result of the planets that the sun hosts and also where it fits in the kind of grand scheme of galactic chemical evolution. So before I get started, I just want to shout out all of the people who've helped put this work together. We have a range of disciplines represented here, starting with our earth scientists and cosmochemists all the way to the galactic folks. So we've been kind of flipping this idea of knowing thy star, knowing thy planet on its head. We're throwing the Milky Way into the mix, and we've had a grand old time. So I'm really excited to talk to you about it. And yeah, we'll go ahead and get started. So basically over the last decade and a half or so, we've noted that our sun seems to appear chemically different from other sun-like stars. So stars that share the same effective temperature, surface gravity, and metallicity as our sun within some uncertainty range. And so this is something that Megan Bedell worked on. We saw this plot earlier in the week, where she looks at, the most sun-like of the stars, so a sample of solar twins, and looks at how their average kind of abundance patterns compare to that of our sun's. So that's what you see up here, and this is all plotted as a function of condensation temperature. So the temperature at which 50% of the element is going to condense from a vapor to a solid. And so you see on the right-hand side here that our sun is looking kind of depleted in these higher condensation temperature elements or our refractory elements, so the elements that make up our rocky bodies. And this has come to be known as something along the lines of the relative refractory depletion trend that we see in our sun. And depending on the type of analysis that's done, the data that are used, we typically see our sun is showing this depletion in refractory elements compared to like 70 to 80% of sun-like stars we've studied. And so the question is why, right? We think our sun is very boring and average in most ways. So why is it showing this depletion in chemistry or in refractory elements? And so there's two ways we can think about this, which is very on theme, I think, for what we've been talking about a lot like earlier in the week, which is kind of disentangling the galactic from the planetary. So we can think about exterior mechanisms like galactic chemical evolution. Is this just a result of that? Or is it something more local, like a solar system process that is creating this chemical depletion we see in the sun? So our groups looked at both, but I'll start with the local processes since we're at Know Thy Star, Know Thy Planet. And this really started with thinking about kind of the main theories in the literature that can explain this refractory depletion that we see. And so basically what we see, or what has been proposed, is that all of the refractory material that was in the solar system has been locked up in the terrestrial planets and the giant planet cores. So that's why we see this deficit in those elements in the sun. Theorists have since kind of deconstructed this and calculated the kind of amount of material needed to make up that deficit, and it far exceeds the amount of terrestrial planet mass we have in our solar system, but nevertheless, we can kind of keep this in mind. And so perhaps a more updated theory from Booth and Owen in 2020 was that it's not the terrestrial planets, it's the giant planets. And so as the solar system is forming, giant planets are kind of carving out gaps in the disk, and these gaps are acting as dust traps. So they're pushing all of the refractory enriched dust beyond their orbits such that the sun can no longer accrete it, and that is what is explaining this deficit that we see. And so these were the two scenarios I was interested in testing using kind of a population scale level analysis. So far, I think a lot of the work that had been done in this space had been done with handfuls of stars, under 100 or maybe 1,000 or 2,000. So really pushing this kind of an order of magnitude higher. And so that's exactly what we do. We do that using Gaia. We use spectra from Gaia RVS. We have spectra for about 17,000 sun-like stars. Of those stars, about 50 of them were known exoplanet hosts. And so we go ahead and use data-driven learning using the Canon, which has also made quite a heavy appearance this week, and infer abundances from those spectra to really push the precision on the abundances we can get and continue, just building out these trends and seeing if the sun continues to sort of look like this chemical outlier, even compared to 17,000 sun-like stars. So we go ahead and build this plot that's very similar to what Megan kind of constructed, and we look at the average abundance pattern of our sun-like stars compared to the sun. The idea being if the abundance patterns match, they're going to sit at this 0 horizontal line here. So if we plop the data down, we see that that's not the case. The sun is still looking refractory depleted compared to our 17,000 sun-like stars. Ultimately, that remains true as well when we consider explicitly the planet host population. So we break up our planet host population into the giant planet hosts to test that giant planet dust trap scenario, and also the terrestrial or small planet host to test that kind of refractory locking up scenario. And neither of those kind of match the sun. They're matching what we've always seen. And so what does this mean? Well, it means, planet architecture effects on host star chemistries, and these different scenarios I talked about could very well be playing out. They're doing their thing, but they're doing their thing at a scale we cannot detect with our medium res spectra. And the fact that we're able to see this refractory depletion really means that we need probably some other source that we can detect that explains, again, this depletion that we can see. Our work also gives us a sense of the abundance precision that's required to tease out these planet architecture effects. It's on the order of 0.01 to 0.02 dex, so really in the high-res spectra regime, which other works have found as well. So we're really back to the drawing board to explain the sun's apparent depletion. And so this is really where we turn to kind of the galactic scale mechanisms. And so we first kind of test galactic chemical evolution, and we do so not by invoking any models, but just looking at how the data behave as a function of fundamental stellar parameters that probe GCE. So we build out our catalog a little bit more. We find some more sun-like stars that have the same abundances measured. We measure the refractory depletion for each of these stars individually, so we can have a metric to look at that's on the y-axis. And then we bin all of these sun-like stars by their metallicity and color them by their alpha enrichment. So again, we've talked about alpha over Fe a lot this week, but as a reminder, this is really a description of the kind of star-forming environment these stars are born in, right? It's looking at your alpha process elements that typically come from your core collapse or type 2 supernovae versus, your iron peak elements that are coming from your type 1a supernovae. And so again, if we put the data down, we can see there's some trends, right, with these two different kind of stellar parameters. And we can see that the sun is sitting sort of at the edge of the mean distribution of our data, so not some crazy outlier, but again, at a place where you maybe might start asking questions. And one thing of note that we really kind of sunk our teeth into is the sun is at this refractory depletion of 0, and the stars that have the same refractory depletion pattern are actually stars that are not solar metallicity and solar alpha, but are slightly more metal rich than the sun and are more alpha depleted. And so this kind of looked and smelled like galactic chemical evolution. And so we wanted to see, does metallicity and does alpha enrichment, can these be used as basically predictors of these refractory depletion patterns we measure for each of our stars? So we asked the question, if we fix metallicity around, say, the most solar metallicity of our stars, do the alpha enhancements or enrichments of these stars then predict the refractory depletion patterns we've measured for those stars? And so the answer is not really, right? We're seeing that alpha over Fe and this refractory depletion slope and trend are flat. There's no real relationship here. But we do see that the sun is kind of within 1 sigma of the running mean. So it's not really a chemical outlier, at least in this space, but maybe that doesn't mean anything since this isn't telling us anything. But we can say, we can take a moment to pause and ask, does this mean alpha over Fe isn't useful at all? Or maybe it's the way we're kind of defining alpha over Fe. And so this question really came about thanks to, again, the range of perspectives we had. I don't think we would have come this far if we didn't have that. And so alpha over Fe, as we know, is an approximation, right? It's a beautiful approximation, again, to help us describe star-forming environment, but it's making this kind of binary designation of elements, saying this element is mostly coming from core collapse supernovae versus this one that's coming from type 1a. When we know in nature, it's more complex, right? Most elements are coming from a combination of both, just at different relative amounts, which is why we make the approximation in the first place. But when we're teasing out these really subtle signatures, maybe those approximations aren't good enough. So here is where I advocate for using this metric instead. This is ACC over A1A, and this is kind of the data-driven version of alpha over FE. So data-driven modeling for the win, making another appearance. But this is coming from Emily Griffith's work that came out last year, where basically she decides she's going to model abundances as a sum of two processes, a prompt process, which we can associate with our core collapse supernovae, plus a delayed process, which we can associate with our type 1a supernovae. And the idea here is, again, we're better modeling that complexity of the fact that elements are coming from both of these nucleosynthetic sources, and we can better capture those complexities with data-driven modeling and see if that does a better job of kind of representing this refractory depletion trend we calculate for our stars. So we go ahead and run this model on our data, and we get out these two metrics. And so ACC and A1A are just describing kind of the process amplitudes for each of these nucleosynthetic sources, where we show that, how much of the star is coming from each of these sources. And if we see if this kind of data-driven ratio does a better job of predicting this refractory depletion, we see that it does. And we also see that our sun is no longer even at the 1 sigma level. It's looking very average. And so here we see, that data-driven learning for, GCE is doing a good job of explaining our sun, and our sun is no longer looking so unique, which, during these unprecedented times, it's a little bit of a relief to know our sun is still boring. So I think, with all of this to say, I think this is a really good application of all the things we talked about this week: data-driven learning, disentangling galactic sources from planetary, and ultimately our sun is boring. So thank you so much, and thank you for the organizing committee for having me.
Questions?
Wow, floored the room. All right.
All the way at the front.
Could you say a little bit more about how this ACC over A1A is actually measured? I understand what alpha is, but...
Yeah, so it's a bit like a principal component analysis. And so basically the idea is you're kind of modeling all of the abundances you have in your star or your stars. You're doing this on a population scale as two process amplitudes, if that makes sense. And the idea is,
Yeah, I mean, so it starts with the abundances, but you just interpret them with two different basis vectors or something.
Yeah.
At the back.
Hi, thanks for your talk. So we've heard a lot about ages, and I keep asking questions about them, sorry. But I was wondering, there's a lot of uncertainty in a lot of the ways that we define ages and try to look at population level statistics. Do you think that this new metric offers, a real improvement on that kind of accuracy or precision? And do you think that it is possible to use those to look at population level trends, or maybe not?
That's what I'm hoping. That's what I'm hoping to sell people on. I don't know. I have worked on ages. I've done a lot of gyrochronology work. I'm very suspicious of a lot of ages. So I like using chemistry a lot more. And so if we're able to use this as a nice workaround, that would be fantastic. Yeah.
Online questions?
From online, in your comparison of the sun to a large group of solar analog stars, can you comment on manganese and its apparent aberrant behavior?
I want to ask a clarification, but is it from my work or just manganese in general?
Unclear.
Yeah, okay. am not sure. I mean, I think I will say, like, the way we're looking at this is, it's a
They
grid.
said the plot you showed earlier.
Okay. Yeah, I think the key here is, like, it's a gradient that we're measuring ultimately. So, like, the individual, it's a very messy slope. It's not like a perfect, you know, trend. But we're just looking at kind of the general gradient. And so, like, the individual outliers don't necessarily make a huge difference because ultimately we're just using this kind of rough metric of a gradient.
And let's thank Raina again.